Hi folks, we're going to take a look at page 2 from Unit 6, Lesson 3. So here we're studying combinations of functions, and we're going to try to use the relationships we found between the arithmetic combinations functions and the original functions themselves to see if we can sketch the graphs. That's what we're doing in number 3. So now here, if you take a look what I gave you the graphs of two functions. I actually also gave you the equations, okay? So that might be helpful, although we'll see how much we can get just by looking at the graphs themselves. Okay, so let's start by f plus g. So f plus g, remember, is defined as the sum of the individual y values for whatever input you pick. So pick an input of 2. It's just f at 2 plus g at 2. All right? So we know that this function's domain is going to be the intersection of the domains of the two individual functions. So for the first three, there's no issues because the domains are all real numbers for both of them. Okay, so the intersection is clearly all real numbers. And even if we take a look at the last one, we know that the denominator can't be equal to 0, but neither of these functions are ever equal to 0. So the domains for all these functions are all real numbers. So that's out of the way. Now, if I want to look for the x-intercepts for when I'm adding two functions occur when the y values have opposite signs. But since they're both always positive functions, these won't ever have any x-intercepts, or the sum won't have any x-intercepts. All right, so let's take a look and see what we can get. Well, first I notice that there's a really nice point. They both pass through 0, 1. So if I'm adding these two y values, I know 2 is going to be a point on the graph. Okay, so let me start here. And since I'm always adding positive numbers, I never have to worry about any negatives. So I'll just put that there. And I know that it's going to have to pass through 0, 2 when I add them. All right, so from here, since we don't have any we're not going to have any asymptotes or holes. Let's take a look at the end behavior. So let's see what's happening. So here, clearly f is this one, okay, and this one here is g, because 2 to the negative x. So what's happening as I move towards positive infinity? Well, I have a really, really big number adding to a number that's getting smaller and smaller and smaller. So big number plus small number still gives me a big number. So it looks as though I'm still going to have this function approaching positive infinity, and I have something very similar on the other side because f is a very small number which I'm adding to a very large number from g. So again, looks like we're going to have function going to positive infinity. Now because these two functions are essentially the same, they're just a flip around the y-axis, a reflection around the y-axis, essentially I should expect this to still be an even function. Okay, because I'm adding the same numbers, okay, just in different order, which won't make a difference, on both sides of the y-axis. So I would actually expect this to be an even function, which of course we could check by actually calculating f plus g at negative x, and I think we'd find that we would definitely have an even function. Okay, so let's move on to f minus g. Okay, now this will have at least one x-intercept, because the x-intercepts occur when f and g are exactly the same, and it looks like the only place that occurs is when x is equal to 0. Okay, so here I'll wait to draw my scale to look at things like signs. So let's take a look again. No vertical asymptotes, no holes. So let's take a look at end behavior as x goes to positive infinity. So I'm doing f minus g. So I have some really big number subtracted by some really small number. So it looks as though this function will go to positive infinity as x goes to positive infinity. But if I look on the other side, f is a very small number and I'm subtracting a very large number. So I'm going to end up with a negative value, and values that are getting, since I'm subtracting an ever bigger and bigger number, looks like that's going to go to negative infinity. So here I'll draw my scale so that it's a little, so that's more towards the center. Okay, and so here what do we have? We know it has an x-intercept at 0, 0, and we said that it was going to go to positive infinity towards the right and negative infinity towards the left. Now exactly what the shape is going to be here, I guess we can't know for sure. Maybe we could plot a few points, but we do know that this is going to be the general behavior of the graph. All right, so let's go to f times g. All right. So again, this will have an x-intercept when either one of them is equal to 0. Again, neither of these functions are ever equal to 0, so I won't have any x-intercepts again. I know that at 0, 1 times 1 is 1, so I'll keep that in mind, that it does pass through 0, 1. So let's see what's happening as I go towards the right. So I'm multiplying a really big number times a really small number. And that's a tough one because, if I didn't have the equations, the question would be, is this increasing faster than that is decreasing? Or is this decreasing faster than that is increasing? And whichever one's going faster would be the one that would be taking over. If this was increasing faster than that was decreasing, we'd end up going towards positive infinity. Whereas if this was approaching 0 faster than that was getting larger, then the end result would be that it's approaching 0. But hey, they're the exact same type of function. They're both 2 to the, in this case here, x or negative x. So they kind of change at the same rate. So what happens? Okay, likely it would be approaching some horizontal asymptote that's not 0. But since we know the equations of the graph, let's see what happens. So this is just equal to f at x times g of x. So in other words, 2 to the x times 2 to the negative x. And of course, here we can just use our exponent rules. This is just 2 to the x plus negative x. And of course, x plus negative x is just 0, which is equal to 1. So in fact, what does this graph look like? It's just going to look like the line y equals 1. Okay? So notice how we had figured out that it was going to pass through, 0, 1. And we had an idea that it would be approaching some horizontal line. In fact, the whole thing is just going to be a horizontal line. All right? So that's an interesting combination of those two functions. So let's take a look at the division. So we already established that there won't be any holes or vertical asymptotes because I'm never dividing by 0. So again, I have f at x divided by g of x. Well, hey, at x equals 0, they're both equal to 1. So 1 divided by 1 is just 1. So it'll still be passing through 0, 1. And let's take a look at the end behavior. Okay, well, we've got on the right-hand side, we've got a really large number, okay, being divided by a really, really small number, approaching 0. What happens when I take some big number and divide it by, say, something like 0.0001? It's going to get even bigger. So it looks like it's going to approach positive infinity even faster than f did originally. Okay, let's go the other way around. As I go to negative infinity, f is some really, really small number, and I'm dividing that by some really, really large number. Well, hey, that's going to make the end result even smaller. So it looks like this is going to approach 0 even faster than f did. Okay, so if I try to draw that, I might even want to throw in what, f looks like, which passes through, 0, 1 and 1, 2. So I know f kind of looks like this. And we said that the new function should be increasing even faster. Okay? Because I'm dividing by this really small number, making it even bigger. And the opposite here is I'm taking some small number and then dividing it by some really big number, so it should be approaching 0 even quicker. So I would suspect my final function would look something like that. Now let's take a look, since we do have the equations, and see if that makes sense. Well, what's f at x divided by g of x? So it's 2 to the x divided by 2 to the negative x, which of course I just subtract them, x minus negative x. And hey, what's x minus negative x? It's 2x. And this now really makes sense, because what did I do? I'm taking my original function and I'm compressing it. So I'm bringing it up even higher and kind of pushing this in. It's going down even faster. Okay, so we were able to make a judgment call on that just by looking at the graphs, and it matches exactly what we would expect for the equations. Okay, so just to recap how you deal with these things. So step number 1 is determine what your domain is going to be. In this case here, happen to be all real numbers for all of them. Okay, step number 2 is start looking for those characteristics. Where do I have x-intercepts? Where do I have vertical asymptotes based on the behavior of the individual functions? And then once you figure that out, then you can look at the end behavior. And what you can get is a general shape for the function. Now notice here I didn't talk about, it sort of came out naturally that this would likely be a local minimum. Okay, that often, unless you're working with maybe trig functions, determining where the local minima and maxima are is going to be a tricky endeavor unless you're working with, unless you have calculus tools. All right, so let's move to number 4 real quick. All right, so here we're looking at end behavior, and we're just going to do exactly what we did before. So I'm just going to draw a quick little graph here. So we have 2 to the x, okay, and then we have x squared. So as x goes to positive infinity, we're subtracting. So what do you have? You have some really big number subtracting another really big number. But this is where you have to ask yourself which one increases quicker. And we know that exponential functions increase quicker than polynomials. And so while I'm subtracting some really big number, this is the one that's getting bigger faster. So it's going to take over. So y is still going to be approaching positive infinity. So let's go to the other side. Here we've got some really, really small number, and I'm subtracting some really, really big number. Well, that one's a no-brainer. We know that y is just going to have to go to negative infinity. So even though this is decreasing more quickly, it's approaching 0. So some really small number minus this really, really big number, I'll be going to negative infinity. That's it, and that's what we do. So now let's go to the next one. So here we have 2 to the negative x, okay, and here again we have x squared. So let's take a look at what's happening as x goes to positive infinity, and we're multiplying these. So you've got some really, really big number, x squared, multiplying by some number that's approaching 0, but because exponentials grow much quicker, this is going to 0 faster than that one's going to infinity. So this one's actually going to take over. The end result is that we're going to be approaching 0. Okay. On the other side, it's a little easier because you got two big positive numbers that are being multiplied. Well, you're just going to be going to positive infinity. Okay. Oops. As x goes to negative infinity, y is going to be going to positive infinity. Okay. And let's do this one here. Okay, so we have log x, which looks something like this. Okay, and then we've got x squared. So here, what do we have? So as x goes to positive infinity, well, you have some number that's getting larger and larger and larger, and then you're dividing it by a number that's getting larger and larger and larger. So what's going to be the end result? Well, the one you're dividing by increases much more quickly. So again, this is going to be approaching 0 because this is the one that takes over. No matter how big log x gets, x squared is going to be much bigger than that. So when I do the division, I'm going to be approaching 0. Okay. Now, we can see that x approaching negative infinity, well, that's not even valid here, because this doesn't even exist as x goes to negative infinity. So I'm not going to consider that. But what I could consider is what happens as x approaches 0, okay, from the right. So I think we've seen this symbol before. This means that I'm approaching 0 from the right-hand side. Well, let's see. This is approaching 0. Oh, sorry, I guess the numerator. This is approaching negative infinity. And then I'm dividing by something much, 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 much smaller. So what happens when I divide, say, negative 1,000,000 by negative 0.00001? Okay, well, what happens there? It's going to make it an even more negative number. Okay, so here, and in fact, by the way, one thing you can always do, didn't even think of mentioning this, is if you're ever stuck, you can pick up your calculator and always check. Well, let me pick some really Let me pick log of, where's log here? Log, oh, there we go. Log of 0.001. Okay, and let's divide that by 0.001 squared. What do we get? Negative, that looks like it was at 3 million. If I pick something even smaller, log of 0.000001, so 5 zeros, you got to remember how many you have, equal, okay, divided by 0.000001 squared, and look what you've got. So our initial assessment that it should be going to negative infinity looks like it makes perfect sense. Okay, so while this is not technically end behavior, it's something to look at because we know that's where the domain ends. Okay, so just to recap this portion here, in order to determine the behavior, the end behavior of these combinations, good thing to do is to sketch both of the functions you're working with, and then depending on the scenario you might be able to easily judge. So for example, if I'm taking a really big number minus something really small, I can easily judge that it's still going to or in this case here, really small divided by really big, I was able to easily judge that it's going to negative infinity. Whereas if I have to make an interpretation, it's going to be by comparing the growth rates of the function. So for example, an exponential grows faster than a polynomial. All right, and then from there you decipher what the end behavior should be. Okay, that is it for this page.